Okay, we should be going. I'll just indicate what we'll do today. We're going to cover the last section on logistic regression, which is section 8 in chapter 14. And then if we have some time left, I will talk about matrix algebra a little bit. Now, Monday is the last day of classes. We may spend a little bit of time on a few things, just mopping up a few things that perhaps I should have covered in a little more detail. But part of the time will be reviewing and also including perhaps looking at some of the assignment problems, but also discussing what will be on the final exam, which will be on the 12th. And so, actually, yeah, today's the 4th, so is that right? So it's Thursday of next week, the final. Okay, so you can download the notes. I may add to them a little bit. There were a couple things I wanted to add that I didn't have quite enough time to get in. So here is the code, which if you download you'll have. I'm not sure. Okay. Yeah, okay. Oh, I see. Actually, I have. Every time you start it up, you have to sort of go through this. It takes you back to your home directory, so you need to go through and just check a few things. I'm going to clear this out. And then I'm also going to clear the console. So let me execute this and I'll give you a sense of what we'll be doing. This is in the chapter on multiple regression and correlation, but it's a different type of regression called logistic regression. Now this goes back to the binomial distribution. And so what we're going to be focusing on is the case that our outcome variable y is binary. Now you can extend this model to the case that y is nominal, that is more than 2 categories. But we're going to be focusing here with logistic regression where there are 2 possible outcomes, which could be yes, no, survive 5 years, not survive 5 years. Any binary outcome. Now, back in stat 511, you would have covered things like contingency tables. So one of the things you might have covered is, the 2x2 contingency table where either the rows or columns would represent the outcome variable and the other would represent a predictor. So you might think of predicting a binary variable from another binary variable. And that would be a 2x2 contingency table. Or you could have a 2x3 where where you're predicting a binary variable from some nominal variable that has more than 2 levels. And that would be another way of looking at the contingency table. You look at it more as a model than you would be looking at it the way it's traditionally done in Stat 211 or Stat 511, which looks at simply test of independence, where you're looking at, is there some dependence relationship between the two categorical variables. What we're going to focus on here is the case where we have a binary outcome, but the predictors are continuous. And that's why it's regression, in the sense that you want to predict the binary outcome. And I'll explain what I mean by that in just a moment. And it's going to be based on initially one continuous x. In fact, that's the only case covered in the book where you have a single x. That's sort of like simple linear regression, except in simple linear regression, both x and y, are numeric variables. Here only x is numeric and y is binary. What we're actually interested in is the probability. If y is the outcome variable, and let's let the two categories be 0 and 1. And so if you were interested in, what you're really interested in is the probability that y equals 1. So for example, if you had an operation or you had some procedure done related to cancer, a lot of times you talk about the 5-year survival rate. And in particular, what you want to know, what is the probability that a patient survives 5 years? So if you go into a particular procedure and the 5-year survival rate is 10%, that's not real encouraging. But if you know that the 5-year survival rate is 90%, that's a lot better. So how would you estimate these survival rates? Well, that's the type of thing. And what would they depend upon? Now, if you were back much earlier in the book, back in the 511 part of the book, where you had a two-way contingency table, you might have two different procedures. And then you look at the 5-year survival rate for each of those procedures, and then you could determine whether one procedure is more effective than the other. But again, that would be a binary x variable predicting a binary outcome variable. So we're going to look at an example in this section where we have, let's see, I don't explain it too well. You basically have patients and you have aneurysms, and you want to know in a certain period of time, there's a certain probability that the aneurysm will rupture. And what of interest in this particular study is whether or not the size of the aneurysm in centimeters is related to the probability that it will rupture. So there's a small data set. It's in the book. The 3.75, they actually give a range of like 3.5 to 4.0 centimeters. And so what we've done here is take the midpoint of that range of 3.75 centimeters. And of the 33 patients that had an aneurysm that was in that range, or let's say about 3.75, none of them ruptured. There were 133 that had aneurysms that are size about 4.5 centimeters, and for those 133, 3 of them ruptured. So this is a binomial experiment. So for each patient, you either get a rupture or you don't get a rupture. So you can view each row there as a binomial experiment. I'm just trying to give you a context for what we're going to be doing. So we have multiple binomial experiments. And we could put this in a 4x2 contingency table, just like that. I mean, that is a 4x2 contingency table, except for the fact that you wouldn't have ruptures in patients. You would have ruptures and non-ruptures. So that second column would be the patients minus the ruptures. So for example, 33 is the non-ruptures for the first row, but for the second row, you would have 130 non-ruptures. And then for the next row, you would have 74 non-ruptures. So that would be a 4x2 contingency table. And you can analyze it that way. But we'd like to get a prediction model. In other words, rather than just saying, is there a dependence relationship between the size of the aneurysm and whether or not it ruptures, we'd like to get a prediction model based on the size. So, but remember, we're actually trying to predict, or we will be predicting the probability that it ruptures. So, we're going to do a little bit more than just do a two-way contingency table. Now, if you're doing a two-way, if a 4x2 contingency table, if you did it that way, there are really two types of tests you could do. If you randomly sampled patients, and if you took the total number of patients, and you randomly assigned them into those categories, that would be a test for independence. But if you were comparing populations, so if the rows would represent populations, that's called a test of homogeneity. So at least conditionally, what you would be doing is a test for homogeneity. If you were again back in step 511, you'd be testing that. You'd be testing homogeneity. But we wouldn't really be using the numerical information we have if we did it that way. We wouldn't really be using the size. It would be as if we just had 4 categories. So we want to do a bit more than that. That's the context of what we're doing. So if you think of this as an extension of contingency tables, or at least an A by B contingency table where B only has 2 levels, but A could have more than 2. It's sort of like that, but we're going to use numerical information for the rows. So, this gets into a little bit more mathematics. Suppose we let pi, not 3.14, but suppose we let pi be the probability of the success, or let's say y equals 1. The probability of y equals 0 then is 1 minus pi. Now we talk about the concept of an odds. The odds of a success is pi over 1 minus pi. But we're going to work with the log odds. And there's a reason why that we work with the log odds. If we were fitting a model, what we're going to say is, if you look down at this equation here, we're going to say that the log odds is linearly related to some x. In this case, for our example, the size of the aneurysm is x. We're going to say it's a linear relationship, alpha plus beta x. So it's like a linear regression, except for the fact that the left-hand side is not just y, which is numeric, but it's a log odds. Now, you might say, why don't we just predict pi of x? Why don't we just predict pi as a function of x? Pi is equal to alpha plus beta x. Why don't we just do that? Can anyone tell me why that's not going to work very well? Is there anything to restrict alpha plus beta x to being between 0 and 1? Pi has to be between 0 and 1, right? So if I said pi equals alpha plus beta x, or pi of x, in other words, pi is a function of x, is equal to alpha plus beta x, I could get a prediction outside of the range of 0 to 1. But if I take the log of pi over 1 minus pi, then that has a range from minus to plus infinity. Okay. So as pi goes to 0, what happens? It's the log of 0. As pi goes to 1, then the ratio is infinity. So my point is that by taking the log odds, I don't have to worry about being outside the prediction range. If I would, well, this transformation, log of pi over 1 minus pi, or log odds, is called the logit of x. Or you can think of it as logging it. But it's the logit transform. Now, in biological assay experiments, we do a slight variation of this. It's called the Probit. It's based on normal theory. It's based on the S-curve of the normal distribution. This is also an S-shaped curve. In other words, if I look at this form, if I solve for pi, if I take this equation and solve for pi, it's equal to 1 over 1 plus e. E is the exponential, 2.718, etc. Goes on forever. It's 1 over 1 plus e to the minus in quantity alpha plus beta x. That's an S-shaped curve that goes from 0 to 1. If I would have had a Probit instead, it would also go from 0 to 1. It's called the cumulative distribution function of the normal distribution. And it starts out at minus infinity at 0, and eventually it gets up to 1. It's an S-shaped curve. This is also an S-shaped curve, but it's a slightly different curve. There are other S-shaped curves, what's called the complementary log, which is used in survival analysis. Again, these three forms, the Probit, the logit, and the complementary log, they have to do with the rate of increase. They're slightly different for these three models. So we're going to focus on the logit. And that's probably, in health sciences, this logit model is probably more common than regression. It's very common. So we're going to be looking at this model. Now, we're going to analyze it as binomials. You actually could analyze this in what's called the raw form, where your data, instead of the data looking like this, you get zeros and ones for every patient. You get a binary outcome, 0 and 1. We're, at least for today, and I don't have the notes written out for the other one, but maybe I'll add it if I have time this weekend. You can actually do it in the raw form, which basically means that instead of having the binomial outcomes, you actually have a 0 or 1. If I sum up all these numbers right here, that's the total number of patients, and for each patient, I have a 0 or 1. Now, sometimes you have the raw data, and sometimes you don't. Sometimes you just have a summary of all patients following this range, but you don't have the raw data. Sometimes you do have the 0 and 1s for each patient. Now, there's some advantage to that, because for each patient, if you had other predictors, in other words, if you have information, demographic information, or other clinical information about that patient, then if you have the raw data, 0s and 1s, we can fit all this other clinical information or demographic information to see what else may relate to the probability of success. Let's say the probability of a 5-year survival. It may be more than the aneurysm size. It could be other factors, or it could be other numeric variables. So if you extend this model, a lot of times you're going to want to use the raw form. So this is the model we're going to be looking at. It's a logit model. We call it procedural logistic regression, or when we're trying to predict the log odds. But of course, what we're really interested in predicting is pi, the probability of success. And that's given in a nonlinear form in this way. And again, that's an S-shaped curve. Maybe I'll add that. In R, we can draw it. It's a nice thing. do all this stuff in a way. Now, if I talk about the probability y equals y sub I, where y sub I is equal to 0 and 1, I claim it's equal to pi of x sub I to the y sub I power 1 minus pi of x sub I to the 1 minus y sub I power. So if y sub I is equal to 1, then the probability of y equals y sub I is pi of x sub I, because the 1 minus 1 is 0, so that second term is 1. If y sub I is 0, then the first term is 1, and the second term will be 1 minus pi of x sub I. So I can write the probability of y sub I for the case of y equals 0 or 1 in that way. Now, do you remember, so what is the probability that y1, that y1 is equal to, that y equals, well, for each y, y1, y2, y3 up through yn, that they take on the values of zeros and ones and so forth. So if I look at my whole sample, not just a single observation, y sub I for the ith individual, but I look at all individuals and I ask, what is the probability of the joint probability? Now that's equivalent to asking, in the simple case, if I have two events A and B, what is the probability of A and B occurring?
A given B.
Why not?
Probability of A given B
times the probability of B. But if A and B are independent, it's just the product of the probabilities. So in other words, if probability of A and B, if A and B, those two events, are independent, then the probability of A and B is equal to the probability of A times the probability of B. So what I claim is, if my sample is random, that is, if the patients are independent of each other, I can write the joint probability as the product of the probabilities. And that's, this symbol right here is the product. This says the product of I equal 1 to n, a pi sub I, y sub I. So it's the product of those. That is called the likelihood function. And it depends on two parameters. It depends on alpha and beta. You may not think about it this way. Notice if I substitute pi of x down here and 1 minus pi of x, it's really now a function of alpha and beta. So in other words, if I substitute pi of x sub I for this, I would get 1 over 1 plus e to the minus alpha plus beta x sub I. So that would get substituted here, and 1 minus that would get substituted here. So this is really a function of alpha and beta. It's hidden, but if you think about how pi is defined, it's defined in alpha and beta, so that likelihood function is really a function of alpha and beta. Now you didn't know this perhaps, but we also had a likelihood. We could think of the regression model as a likelihood function. And then, which was a function, in the case of simple linear regression, of alpha and beta. And it turned out, because of the simple nature of the normal distribution, which doesn't happen to have the binomial, it turned out that the form of the likelihood is very simple, and it actually allows us to easily get the estimates in terms of a linear system of equations. Now, put it another way, we don't usually work directly with the likelihood. We generally work with the log likelihood. In this case, the log of a product is the sum of those. The log of AB is the log of A plus the log of B. So instead of working over a product, it's usually much easier for us as statisticians to work with sums. So by taking the log, we turn products into sums. And so if I take the log of this quantity, which I'll call big L of AB, it's now written as a sum of these things. Remember that if I have the log of pi to some number y, that's y times the log of pi. And that's why, in other words, pi to the y, if I take the log of that, that'll be y log of pi. And that's why you get like y sub I log of pi, and here you get 1 minus y sub I log of 1 minus pi. So that's where that's coming from. It looks complex, but it's really just the fact that the log of pi to the y is y log of pi. And the log of 1 minus pi to the 1 minus y will be 1 minus y log of 1 minus pi. So, and the sum is the result that I have a product here, and if I take the log of a product, but I also have a product here, so I'm getting the sum. I'm getting a sum here for everything as well as a sum for these individual terms. Now again, what I didn't show with regression, that if you have the log likelihood and you take the derivatives, and again, I'm not assuming calculus in this course, so don't worry about it if you don't see how this occurs. But if you take derivatives and set them equal to 0, in the case we had for multiple regression, we got a system of what was called normal equations. And those normal equations were linear equations. So we had if we had 2 parameters, we had 2 equations and 2 unknowns, and we'd solve for alpha and beta. It would be very simple. If we had more than 1x, say we have kx's plus the intercept, we would have k plus 1 equations and k unknowns. But again, they're linear. It's very easy to solve. Well, relatively easy. Here, these are nonlinear. When we take the derivative of this and set it equal to 0 to find the solutions for alpha and beta, we take the derivative with respect to alpha and the derivative with respect to beta. And we set it equal to 0 and we solve for alpha and beta. Unfortunately, this is not so easy to solve because it's nonlinear. In this case, we have 2 nonlinear equations and 2 unknowns. Now, there was a key little prefix, non. If I say we have 2 linear equations and 2 unknowns, that's trivial. If I say I have 2 nonlinear equations and 2 unknowns, not so easy. Fortunately, we have a computer, and a computer can do it for us. So the book, the method shown in the book, and I won't go through the details of that, is called Newton-Raphson. You start out with an initial value. In this case, we'll start out with the case that beta equals 0, and alpha will be the overall proportion of patients that in this case, alpha would be the overall proportion. If I sum this and sum this, it would be the overall proportion of patients that have a rupture. And we could estimate our initial alpha that way, and we'll have our initial beta to be 0, and then we're going to iterate this process. So I won't go through the details. The book actually does, so you can look at it if you're interested. But my point is, it's not a simple. It's not quite a very simple test. In fact, for Newton-Raphson, you have to take what are called second derivatives, and then you do an update where you start out with this initial value, and then you multiply the inverse of this second derivative matrix, times these quantities, and you get an update in a new estimacy of parameters, and you iterate this process until it converges. So again, you can look at the book for that. Now, what are we interested in testing? We'd be testing that beta equals 0. That would be the main thing. Is there a relationship with size? If beta equals 0, no, there's no relationship with size. It doesn't depend on the size. So we're interested in testing, just like we were for linear regression, that beta equals 0. So how do we test it? Well, we test it by what's called a likelihood ratio test. The likelihood ratio test is minus, these are natural logs by the way, minus 2 times the log base e of the likelihood constrained by the null hypothesis over the likelihood unconstrained. So in other words, if I look at the model, under the null, the log odds are simply alpha. And under the alternative, the log odds is alpha plus beta x. So if I look at the likelihood that's constrained by the null, So I have this likelihood, but beta's not in it, only alpha. This likelihood is actually this. I have the log of the ratio, but the log of the ratio will be the difference in the logs. It'll be the log of the top minus the log of the bottom. Okay, so if I have a log of a quotient of a, so I have a likelihood that's constrained by the null with a likelihood that's unconstrained. If I take the log of that, it'll be the difference in the logs. So it's sort of like a product. The log of AB is the log of A plus log of B. The log of A over B is the log of A minus log of B. You can think of it as being A over B. You can think of it as A times B to the minus 1. So if I take A times B to the minus 1, I get log of A minus the minus 1 comes down log of B. So like taking a reciprocal. So the test statistic is D, which is an approximate chi-square distribution. And it only actually has 1 degree of freedom, since I'm only talking about one parameter difference. So that's going to be our test statistic. Now there's another type of test called the Wold Test. And that simply takes the maximum likelihood estimate and gets the standard error of the maximum likelihood estimate. The book didn't tell you how you get the standard error of beta. You can actually get it as part of the Newton-Raphson. But the nice thing is you're going to see that when you fit a model in R, it's very straightforward to get the standard errors because it gives us part of the output. So I could also test that beta equals 0 by getting the estimate beta hat divided by its standard error. This is actually approximately normal. This is approximately standard normal if the sample size n is large. And I could also get confidence interval on both beta and alpha. And we're most interested in beta as beta hat plus or minus the z-value times the standard error of the beta hat, or the estimated standard error. So that's the context of what we want to do. This principle, this likelihood principle, is very central to statistics. And I was thinking about perhaps one of the most effective ways to teach calculus is to do it within the context of data and using R. Actually, you can actually do things like differentiation in R. But the key thing is people learn these rules for doing integration and differentiation, and they don't really have a concept, perhaps, of what this really means. But in R, you can actually show graphically exactly what it means. Well, you can do it anyway, but in R, it's particularly nice because you can actually also relate it to data at the same time. And so, perhaps we're not really teaching calculus quite the right way. Because I think a lot of people go through calculus and they kind of memorize things. And then they don't really understand it deep, conceptually. They don't understand it perhaps as a limiting process for differentiation. But perhaps they don't understand it geometrically. And it's not too hard in R to actually do all this. And I thought about writing an appendix that actually would do that. And if you put it in the context of real-world examples, then you're more likely to remember it. At any rate, in a statistical sense, we can think of, when I say we have a log likelihood, and we choose alpha and beta to maximize the likelihood function, or equivalently, the log likelihood, that's an optimization problem. Now, I showed you an optimization problem last time where you had a polynomial regression. In this case, it was a quadratic. And I said, what is the x that gives a maximum yield? That's a simple example because it's very, very easy to differentiate a polynomial. In particular, it's very easy to differentiate a quadratic. So if I have a function that's quadratic, then it's very, very easy to find the max or the min, whichever the case may be. Well, getting back to this, let's now look at the example. So we have ruptures, and we want to know whether or not the probability of a rupture depends upon the size of the aneurysm. There are a couple ways we can represent this model, but you'll notice one big difference in the model. GLM, not LM. GLM stands for Generalized Linear Models. Now, unfortunately, back in the late 60s, SAS created this PROC called PROC GLM. For them, GLM meant general linear model. There's a big difference between general linear model and a generalized linear model. A general linear model is really just a linear model. Now there's some, as I said, as long as you realize that distinction, it's not to say that SAS can't do generalized linear models. It can, but PROC GLM is not the one you use in SAS to do it. So in R, we use GLM, meaning generalized linear models. And notice that the left-hand side is actually a matrix with two columns. Now there is another way we could represent the data. We could represent it as a ratio of ruptures over the total number of patients. In other words, we could represent it as a ratio of ruptures over the patients. So 0 over 33, 3 over 133. But that isn't going to cut it because we still have to know what n is for the binomial. And so you actually would have to represent, you would have to express it. You would actually also have to say, okay, n equals that last column called patients. So in other words, you don't get away, you can't just use it as a proportion. That's not enough to fit the model. You actually need to know the sample size, the number of patients for each of the groups. So we're going to just do it this way. Notice on the left-hand side, I have C-bind. That combines vectors into a matrix. This matrix will actually have 4 rows representing the 4 aneurysm sizes and 2 columns. The first column will be the ruptures, and the second column will be patients minus the ruptures. So what is the second column? It's the non-ruptures, right? So the ruptures and the non-ruptures, and tilde size. So we're going to model that as a function of size. But notice we say family equals binomial because the default would be normal. A generalized linear model is a family of models. It includes the normal. It includes the binomial. It includes the Poisson regression model. So I have to tell it that this is a binomial problem. We have a binomial experiment. And I said data equals rupture, although, well, if you attach it, you wouldn't really need to do that. So I fit this model, and I'm going to call it logit ruptures, and then I can do a summary. If I do a summary, I get the coefficients right here, and I get their standard errors, and I get their zeta. This is a Wold test right here. That's the Wold test. So if I look at the Wold test for beta, which is the estimate, the beta is actually the estimate for size. And notice that the standard error is 0.394, and the z-value is 2.55. And you can see it's almost significant at the 0.01 level. So it's pretty significant. So it appears that there's a fairly strong relationship between aneurysm size and the probability of a rupture. Now, we get a set of residuals, but the residuals, we're talking about a binomial here, so the residuals are not like the residuals from regression. The residuals are actually called the deviance residuals. And again, we can do diagnostics on the residuals to sort of see if the model is okay. There are a lot of things that could go wrong. Maybe that logit is not linear, for example. You typically don't have outliers because the y sub I is 0 or 1. Although if you get y, if you get y sub I is 0 or 1, you can't have a way out value. But if I actually do a binomial, if I get things very near 0, if I have a lot of trials and I get no successes, then the logit could be extreme. Or if I get something near 1, then again the logit could be extreme in the other way. So, there are issues that could happen. The other thing that could happen is that the fact that I use a logit transform maybe isn't the best thing. Maybe it's the complementary log transform that would be better. So there are issues that could happen with this model that you should be aware of. So if we look at the null deviance, it's 8.14, whereas the residual deviance for fitting the model. This goes back to this whole idea of this likelihood constrained and unconstrained. I use D actually as a representation of deviance. And so this gives us the outcomes we want using the Wold Test. Now, if we go back, and let me just run this inside here. I did a summary of logit rupture, and that's what we had, but I could also do ANOVA on logit rupture. Okay. And in this case, it gives that residual deviance. If we did it this way. Notice it says the link is the logit. In R, you can specify that the link is Probit, or complementary log-log, what's called C-log-log, I think. So, again, the ANOVA function works, but you notice that that's exactly the same results that you got here. And we could actually use those results. We could actually use those results to get the likelihood ratio. Now, if we were doing this, you might ask, well, what does our prediction model look like? So I'd like to be able to plot. I'd like to be able to plot the outcome. And in particular, I'd like to be able to plot the relationship between size and the proportion of ruptures over patients. So what I'm going to do is I'm going to plot ruptures divided by patients tilde size. Okay, so this is saying y tilde x, So that takes the ratio of rupture to patients tilde size. And data equals rupture. And I'm going to specify the limits. The x limits will be 3.5 up to 6.5, and the y limits will be 0 to 0.1. You might say, well, why don't you go 0 to 1? Well, because we're in a small range. In other words, if you look at the proportions, none of the proportions are very high. But you will see, in other words, the bottom one, for example, is 0.1. 6 over 60. But you do see this actually will plot the points, which are these 4 points. That's the raw data, those 4 points. But I plotted the y as a proportion. Ruptures over total number of patients. So I'd like to see how well I fit this model. Now remember, so I'm actually interested in this form right here, pi of x equals 1 over 1 plus e to the minus alpha. So if the log of this is the logit of x, then what I'm actually interested in is the inverse logit. In other words, I'm interested in the inverse logit. The inverse logit of the logit of x is x. I mean, pi is pi. The inverse logit of the logit of pi is pi. So if I actually solve for that, I would actually get this. Well, it so happens there was a reason why I loaded the package Faraway. And that is because it has the inverse logit in it. In other words, I want to represent the data on the original scale in terms of a probability, not the log odds. I mean, you don't have to, but so if you look at, what I'm going to do is this is my model, 8.436 plus 1.0024 times x. That's my model. Where did that come from? There's a minus sign in there, right there. It came from here. So what I have is, I'm going to create x, which is going to be a sequence from 3.5 to 6.5 in increments of 0.1. So I'm actually going to estimate it at 3.5, 3.6, 3.7, 3.8, all the way up to 6.5. I'm actually going to get an estimate. But I want to draw this as a line. Since I'm so close together, it looks like a nice smooth curve. So I side lines of x, and notice the function is the I logit, the inverse logit of my equation alpha plus beta x. And again, x takes on the values of 3.5, 3.6, 3.7, all the way up to 6.5. And the lines actually draws it as a smooth curve on the graph. So that's the curve, that's the fit. You notice it's pretty good. So that's the gist of logistic regression. And I was just trying to give you an appreciation for it. There are other things that we could do, and if I have time, I may add a few more things to these notes, just for your reference. But again, one of the other things to realize, as I mentioned, and maybe I'll add an example along these lines, is instead of having the binomial data like this summarized within 4 rows, I could start out having each row as a patient, and therefore I'd have a lot more rows. Whatever the sum of those 4 numbers is, would be the number of rows you would have. and you have zeros and ones. You can actually use R to solve this particular problem. And if we did this, we would have to have the size for every patient. As I mentioned, that 3.75 is actually a range going from 3.5 to 4, and 3.75 is in the middle. In reality, in real life, you would probably have a more or less exact measurement for each patient. So it wouldn't be 3.5 for all these patients. It might be 3.7 for some and 3.6 for others and so forth. So if you had the data in that form, it would be slightly more accurate. And in addition, you might measure other characteristics on the patients. Characteristics relating to their medical history and maybe even demographic data. And maybe you could actually even have categorical variables like gender. Does the probability of a rupture depend upon gender? And so forth. So that's sort of like the analysis of covariance, right? Where you have numeric variables and you have categorical variables in the same model. And you can do this, of course. So in the course categorical data analysis, you would get into more complex models like this. But this just gives you an idea. So are there any questions on this? Okay. So as I mentioned, this is extremely important type of model. And a lot of times you should realize that earlier, for example, we talked about transformations. And a lot of times it may work that the transformations are helpful, but rather than doing transformations, there are other things you might try. Like if your outcome data is counts, you might do it as a Poisson regression, which is another type of regression. You might do it as a nonlinear regression, and I mentioned this last time. So these other types of models are all important. I realize that I think nonlinear regression needs to be added to this course because I realize that in our curriculum that nonlinear regression kind of gets skipped, and that's a mistake. It may be covered in some of the more advanced courses somewhere, but it's typically, I don't know, well, none of you would have had 545. I'm not sure whether it's in 545 or not. So are there, I know Faraway's book doesn't have nonlinear regression, and that's the book that's used in 545, so I'm guessing that maybe it's not there. Are there any questions? Okay, let's see what time it is. 12:30. I still don't have too much time. Let me just quickly you should I keep not getting to this. But I did give you, oh, I didn't mean to do that. I meant to do this. You should review this. I just wanted to show you a few things. By a matrix A, which typically we represent a matrix in bold, this is a matrix that has n rows. Blow this up a little bit. Has n rows and p columns. That's called an n by p matrix. We sometimes is represented in square brackets as a sub ij. And a sub ij refers to the element in the ith row jth column. So in R, you can create a matrix with the function matrix, unsurprisingly. So here's a matrix, and this says it's 3 by 3. Now in R, by default, R creates a matrix column by column. So if I have the data that way, and let's suppose I'm going to name the rows, suppose this data actually represents bulls bulls, cows, and cows with calves, and the V's represent three different vegetation areas in Montana. And so, for example, in the 3 areas in Montana, there were 98 bulls in vegetation area 1, and 24 and 2, and 42 and 3. And so that's the little matrix. It's a 3x3 matrix. Now notice that it was filled in by columns. So if I look at this order, it fills in the first column, then the second, then the third. I can add matrices, which simply adds corresponding elements. So if I do the same, that was in 1958. So if I do the same thing in 1959, and I add the 2 columns, I'm sorry, this is B. So this is B, this is for 59. And if I add the 2 columns, that simply adds it by element. So that 55 plus the 98 will give 153, and so forth. So if you look, you'll see that corresponding elements are added. You can also take the difference. A minus B is the change from 1958 to 59. That would be a change in the number of bulls. The bulls and cows and so forth for each of the vegetation areas. I could also multiply every element in a matrix by a scalar, which simply multiplies, each individual element. The really important operation is this matrix multiplication, A times B, and that what you would do is take what's called the inner product of, let's say, the ith row of the jth column, the ith row of A times the jth column of B. And what it does, if you take the ith row of A and multiply it times, do an inner product with the jth column of B, I multiply corresponding elements. So the first element of the ith row with the first element of the jth column, the second element of the ith row with the second element of the jth column, and so forth. I multiply them together and corresponding elements, and then I add them up. And that's what I'm representing here. Matrix multiplication in R, so let's suppose that I'm looking at the number of U's having lambs in 1952 and 1953. By the way, the number of columns of A must equal the number of rows of B in order to do matrix multiplication. Otherwise, I couldn't take that inner product. So here I'm representing the number of U's. Suppose I'm representing sort of the number of U's for 1952 and 1953, and I can do this as a matrix. So this would be the ones, there would be 58 U's in 1952 that had no, there would be 58 lambs in 1952 that didn't have U's that also didn't have them in 1953. But there would be 26 lambs in 1952 that did not have U's that did have them in 53 and so forth. So this is a matrix representing the change, or if you went from a single U in 52 to none in 53, there were 52 lambs in that category. Suppose I want to know the total number of lambs if I simply multiply by a vector. This is matrix multiplied by a vector, 0, 1, and 2, because that corresponds to none, single, and 1. If I multiply A, and this is matrix multiplied, notice that if I do scalar multiplication, I simply use an asterisk. But in order to do matrix multiplication, I have %, and that means matrix multiplication. So if I have a 3 by 3 matrix and multiply it by a vector that's 3 by 1, then I get a 3 by 1. And in general, if I multiply an A by B matrix, if I would multiply an A by B matrix times a B by 1 or a B by C, then I would get an A by C matrix. So in this case, when I matrix multiply, I get a 1953 total of this. The transpose simply interchanges rows and columns. So if I take the transpose of A, in an R you just use T for transpose. It just transposes. If you compare that matrix to this one, it flips rows and columns. Now the inverse is interesting. you know, if I say that, okay, the number 2, and I ask you what the inverse is, then what I'm really asking is, what number do I multiply 2 by to get 1? Well, the answer is the reciprocal, or a half. So it's sort of a concept that's similar. If I have a matrix A and I say, well, okay, is there a matrix B that I can, if I take A times B equals the identity matrix. The identity matrix looks like this. It has all 1s on the diagonal and 0 every place else. So if AB equals the identity matrix, then B is said to be the inverse of A, and we denote it by A to the minus 1. That's one way it's represented. Depends on the book. But A to the minus 1 would be the inverse of A. So in R, you can simply get the inverse of A by the function solve. Now, solve actually can take 2 arguments. It can actually solve a system of linear equations. So if you give it a matrix, comma, a vector, that's like AX equals Y, and it solves for X. But if you simply say solve of A, where A is this matrix, and a square matrix, then it will give the inverse of A, and we'll call it B. And just to prove to you that solve of A is B, so B is A inverse, and if that's true, then I should be able to multiply A. Notice I'm matrix multiplying A times B, and that's the identity matrix. So in fact, it is the inverse. So this is the way you do it in R. There are a couple properties that if you take A inverse and transpose that, it's the same as transferring A and then inverting. In other words, the order of doing that doesn't matter. A inverse transpose is the same as A transpose inverse. It's also true that the inverse of the inverse gets me back to A. So what I'm showing here is T of solve of A. What is that? That's the transpose of the inverse of A is this. Here I'm doing it to reverse, the inverse of the transpose of A. But notice they're the same. I was just representing this property right here, that I was representing property 1 up here. By the way, I can subset a matrix. If I say A 1 colon 2 comma 1, this says 1 colon 2, it means it's a list. I mean, not a list, but it's a vector of 1 and 2. And then and so I'm taking the first 2 rows and the first 2 columns. And you can see that's what's called a submatrix. So in R, it's very, very easy to get submatrices. The determinant is kind of a measure of the volume of the matrix. It has actually a statistical meaning. It's related to the covariance structure of a bunch of variables. But we can also use it for other purposes. You know, I said that if you have a matrix A that's square, there may or may not be a matrix B such that AB equals the identity matrix. If in fact A is singular, you won't find a unique inverse. And we call that a non-singular. We call it singular when that occurs. Or sometimes we say there's a singularity. Now, this determinant of A is the sum of minus 1 to the I plus j, where we're talking about row I and column j, and this is A sub I j times the determinant of capital A sub I j. Capital A sub I j is a submatrix found by deleting the ith row and jth column from the matrix. So capital A sub I j says you take the ith row, jth column, you delete them, you get a submatrix that has 1 fewer row and 1 fewer column. Of course, to define the determinant of that, in other words, if I had a 10 by 10 matrix, I've gone from a 10 by 10 to a 9 by 9. That's still a hard. And then you've got to find a bunch of those because I sum, from j equals 1 to n. The point is that's if you did this by hand, you wouldn't want to do it. About the biggest would be a 3 by 3. You don't want to do this by hand. But fortunately in R, there's a function called det for the determinant of A, and the determinant of A is 17,116. There are some properties of determinant. Determinant of the product is the product of the determinants for A and B square. Determinant of A is transpose is determinant of A. Determinant of a constant times A is c to the n times determinant of A. And the determinant of A is non-equal to 0 if and only if A is non-singular. So we have these properties of the determinant. We use determinants in a couple of contexts. One of the areas we use it is to identify what we call singularities in our data, or more realistically, not singularities, but near singularities. And statistically, that means that I have collinearities in my data. I have some variables that are almost linear with other variables in the model. And this can be a serious problem in regression. If my predictors are collinear, you have an unstable regression model. And one of the ways you can discover this is by the determinant. There are a bunch of special matrices. So, for example, a diagonal matrix, you simply have elements on the diagonal and zeros on the off diagonal. You can have an upper or a lower triangular matrix, which means your elements that are non-zero in the upper or bottom part, but not both. The symmetric matrix is very common. It means the transpose of A is equal to A. It means if I flip the rows and columns, I get the same thing. Positive definite says that x prime ax is greater than 0 for any x not equal to 0. And semi-definite can be greater than or equal to 0 for any x. Orthonormal is if the inverse is equal to the transpose. That's a real nice situation. You simply transpose to get the inverse. And an idempotent means if I square the matrix, which means I multiply A times A, I get A back. So you might think that idempotency is kind of a strange thing. But I can tell you the basis of the analysis of variance and the basis of linear models is based upon symmetric idempotent matrices. You know, when we had analysis of variance, we could break up the sum of squares into various components. So I have a regression sum of squares and I have an error sum of squares. And that the sum of those two would be the corrected total sum of squares. So I could take the total sum of squares and partition it into a regression sum of squares and an error sum of squares. Turns out that all three of those can be written as quadratic forms, and the matrices of the quadratic form, which is this thing, those matrices are symmetric idempotent matrices. Geometrically, what that means is if I have this space and my data lies in this space, and I have this plane that maybe represents the regression plane, if I have a vector y, which is my outcome, and I project it onto this plane, so that's actually what I do, and I project it orthogonally, which is these squares. And then this vector is y hat. This is the residual y minus y hat, but this is in n dimensions now. And what happens is that these projection matrices that project y down that plane are symmetric idempotent matrices, and that is the basis of the whole idea behind linear models. Again, I'm saying that, if you didn't understand a word I said, don't worry about it. But if you did, it's interesting. It's not something you'll have to know for the exam. But again, symmetric idempotent matrices are central to linear models, particularly with normal theory where you have these orthogonal projections. So, I guess I'll stop here. I just want to point out that you might want to what I did here with this air pole, this is a regression problem. And, you know, I'm trying to do a prediction. I think the prediction is for SO2. You have rainfall, education, and non-white populations in these different cities. And I think you're trying to predict the SO2 concentrations from these other X variables. And what I did here is I do everything using matrix algebra. Instead of using the built-in R functions, I did everything from first principles using matrix algebra. So that maybe is a good way for you, if you want to learn a little more matrix algebra, and you want to see how it relates to what I did, you might take a look at this example. Okay, any questions? It's time.